Welcome to Ada Core University. My name is Quentin Oshem, and today we're going to see how to write function in Ada, also known as subprograms. Let's get started. Subprograms in Ada are what is referred to as functions or methods in other languages. Ada differentiates two kinds of subprograms: functions and procedures. The difference is that function returns a value while procedures do not. Subprograms are usually split into two parts: the declaration, also known as the specification, and the implementation or body. The specification contains all the information required to be able to call the subprogram: the subprogram name, the parameters, the return type, and the body will contain the actual code of this subprogram, the actual operation and instruction to be performed. In this example here, I have a function f specified. Notice the semicolon at the end of the declaration after the return type. In the body, I'm restarting from the same specification, but instead of a semicolon, I'm writing is, which is opening a declaration block. I can then declare variables, and when I'm done with declaration, write the begin reserved word to start a sequence of statements. In this very case, I have a return statement at the very end of the function, returning a result to the caller. One important piece of information for Ada subprograms. For functions, that is to say subprograms with a return type, when calling such a function, the result has to be stored somehow, in a variable for example. It cannot be ignored. You may have noticed already that sometimes there is a modifier in front of the parameter type. This can be in, out, or in-out. This specifies the mode of the parameter. How is it going to be manipulated by the subprogram? Is this just an input? Is this an output? Or is this some kind of a variable parameter, an input-output that we want to modify within the subprogram and propagate the modification to the calling context? Let's see those one by one. In is the default mode. So if you do not specify any mode in front of the type, it's going to be in by default. It means that the actual parameter is not modified. It's a constant parameter from the subprogram point of view. It's an input. Therefore, only read operation will be allowed. Out is a result. So it is expected that the subprogram modifies the value of the parameter. As a matter of fact, it's even more than that. It is expected that the subprogram initializes the value of the parameter. A common Ada programming mistake is to forget to do this initialization and to return an uninitialized value to the caller. In-out means that the parameter is input-output. It has an initial value coming from the calling context. The subprogram can modify this value, and the modification will be propagated to the calling context. You might have noticed that I've specified the mode according to the way the parameter is to be used by the subprogram, not according to the way it's supposed to be passed to the subprogram. In other words, At no time did I say that I wanted a parameter to be passed by copy or by reference. And as a matter of fact, this is going to be a language or a compiler decision, not a programmer decision. Some types are always passed by copy. Those are elementary types, such as scalars. Certain types are always passed by reference. This is the case of unconstrained arrays. Some types have an undefined parameter passing mechanism, which could be either copy or reference, and the actual mechanism is selected by the compiler based on a performance assessment. For example, small objects will be passed by copy, while bigger objects will be passed by reference. As a matter of fact, this choice will depend on the architecture. Something that may look big on a 32-bit machine may be small enough on a 64-bit machine to justify a copy instead of a reference operation. This is one of the many reasons that makes the Ada language highly portable from platform to platform. The compiler will be able to perform this optimization depending on the actual characteristics of the final target. For further reference, here is a list of what the language says on what has to be passed by copy, what has to be passed by reference, and what is left to the implementation decision. We haven't seen most of this, so I will not go into the details here, but later on, if you want to get back some information, you can come back to this slide. Now that we've seen how to define those subprograms, let's have a look at how to call them. There is a couple of things specific to Ada here. First of all, when calling a subprogram that does not have any parameter, there shouldn't be any parentheses next to the call. So in the case of a function, it looks a bit as if the function was actually a variable. When calling a subprogram, while it's possible to use the regular positional notation, providing a value for the parameters one after the other, it is possible to name the formal parameter that is being provided a value to. When doing that, the order in which the parameter are provided a value does not matter anymore. So, for example, in the second piece of code here, P has three parameters, A, B, and C, and when I'm calling P, I'm providing a value to B first, then to C, then to A. Lastly, if the parameter mode is out or in-out, at call time, I need to provide an object for the value of this parameter, a variable for example, in order to be able to store the result somewhere. It is possible to provide a default value or default expression to parameters that are in the in mode, so input parameters. This default expression will be evaluated at call time if no explicit value is given. Using the name notation, it will be possible to use the default value of an arbitrary parameter in the list of parameters, not necessarily the last ones. It is perfectly possible to use indefinite types as parameter or return type of a subprogram. Text string, for example. In this first piece of code, I'm taking a string as parameter, and then I'm returning the concatenation of this string with other strings. The constraint of the returned object will be evaluated at the point of call. One word of caution again with regards to arrays. It is most of the cases a mistake to assume boundaries for the array. In this second piece of code, in init, I am receiving a string which is called stnt, and then I am iterating over this string elements to reset the values of the elements to space. And I'm doing that assuming the lower bound of the string to be 1. However, as you can see here at call time, I am using a slice of the array from 4 to 6, so the boundaries of the string within the procedure is from 4 to 6, and my loop is going to fail on an exception. Aliasing is an interesting problem. It happens when two names refer to the same piece of data. It's quite common when using references or pointers to indeed have two of these pointers or references pointing to the same data, but this might happen as well when passing parameters to a subprogram. This may cause a lot of problems because in these situations the developer thinks is manipulating two distinct objects, while under the cover there is only one object being manipulated. If you look at languages such as Spark, which are aiming at demonstrating formally the correctness of an application, any case of aliasing will stop the analysis. So it's important to avoid this as much as possible. Ada offers specific features to warn you in the case of the most obvious aliasing issues. In this piece of code, I have an obvious aliasing. There's a variable called 1 for one variable, and a variable called 2 for the second variable. And I am going to modify the value of those variables calling the change function. X and Y are passed as in-out mode, which means that within the function I'm going to allow the modification of X and Y. When I call change twice on the one variable, I am creating an aliasing situation. Within the function, X and Y will refer to the value of 1. And when exiting the function, the value of X and Y will be written to 1. But which one is that going to be? Am I going to retrieve the value of X first or Y first? As a matter of fact, in this case, the language says that's the choice of the compiler to evaluate parameter from left to right or the other way around. So I have no way of telling, and surely this is not something that is clearly understood by the developer. The second case is even more interesting because I have additional questions coming from the order in which operands are evaluated on arithmetic expressions. In all cases, this is highly discouraged. The compiler will provide sensible warning in these situations. Overloading is a technique that allows to provide several signatures for the same subprogram name. It is very convenient when you want to do something a little bit different depending on the parameters that are passed. For example, here I have a print subprogram, and in my design, print should be printing something on the screen, and I should be able to use the same print name whether I'm using an integer object or a float object. So I am providing two versions of this print subprogram, one that takes integer and one that takes float. The compiler will automatically select the correct print method depending on the calling context. Subprograms can be overloaded following several criteria: the number of parameters, the type of those parameters, and the resulting type in the case of a function. And that's it. So other aspects of the specification are not eligible to qualify to an overloading. For example, if you have two subprograms with the same parameter types in the same order but different parameter names, that will not create an overloading situation, and the compiler will refuse to compile the second subprogram because it will have an ambiguity. We haven't seen subtype yet, but in the case where two subprograms are only different from the subtype point of view, that will be refused by the compiler. Different mode will not create an overloading situation either, and the presence or absence of default expression will not be taken into account. These rules are supposed to minimize the situation where there is an ambiguity when calling a subprogram. However, there are still situations where that might happen. Let's take this example. I have two integer-based types, apples and oranges, and I'm overloading the print subprogram. One is able to print apples, the other one is able to print oranges. Now, if I'm calling using a typed variable, like NA, which is a number of apples, the compiler will be able to select properly the version of print that knows apples. However, if I'm calling print with a literal that may refer to an apple or an orange, 0 for example, then the compiler will not be able to discriminate and select the proper print. This is an ambiguous call. In this very case, to work around this ambiguity, there are two solutions. The first one is to qualify the literal value. If I write orange tick of 0, I'm saying that I'm writing the literal 0 that is qualified as being of type oranges. Then there's no problem selecting the proper print. The other thing that I can do here is to provide explicitly the parameter name. Because they differ from one procedure to the other, the parameter name will be used by the compiler to discriminate and select the proper subprogram. One of the very common situations when using overloading is to overload operators, equal, different, multiply, divided, etc., etc. So, as a matter of fact, overloading allows me to modify the existing versions of those operators. It will allow me to add new ones or to remove existing ones. Here, in this very case, I have distance and surface, which are both based on floating point value. By default, there is a multiplication between two values of type distance that returns a distance. But in my context, this operation doesn't make sense. I want the multiplication of distance to result into a surface. So in order to remove this specific operator, I'm saying that the function multiply that takes two distance in parameter and return one distance is abstract. This is not to be confused by the abstract notation of object-oriented programming techniques that we will see later on. In this case, this is removing an operator from the operations available for the type. I'm doing the same thing for surface, and then I am introducing a new multiplication between two distance that returns a surface, so that I'm ensuring some level of consistency in terms of dimension analysis. Note that GNAT offers some specific features for dimension analysis, but this is outside of the scope of the discussion right now. The second example shows a case of overloading the quality operator. In this type R, there are two fields, two components, only one of which should be used when answering to the question, are those two types equal? which is why I am overloading the equality and implementing what it actually means in my context. One note, when overloading the equality, there is automatically an inequality that is going to be generated as well, which is the negation of the equality. Let's get back to subprogram implementation. It is possible to nest one subprogram within another subprogram, as to have some kind of a local subprogram. This nested subprogram will have access to the parent data that are declared before its own declaration. It will have access to the parent subprogram parameters as well. So in this example, I create a nested subprogram which is conveniently called a nested, which is doing some computation based on the W variable from the parent subprogram and the V parameter of this parent subprogram. Nested can be called within P, but it will cease to exist as soon as I exit the scope of P. Two special forms of subprograms that are useful to know. A null procedure is a procedure that doesn't have any instruction. It can be written directly at the specification time with the isNull completion. A function can be used for nothing else than providing a name to an expression. This is used a lot when doing contract-based programming, as we will see later on. You have an example of such an expression function in the second piece of code in this slide. Let's now verify your understanding in a quiz session. For this question and the next, if you think that there is no error in the code, click on the green icon next to the yes. If you think that there is one or more errors in the code, click on them. Once you're sure of your answer, click on Submit. The return value of a function has to be stored, even if no use is made of this value later on. So in this case, this code is incorrect. I am not storing the value returned by f. V is an input variable. It is read-only, so I cannot make any modification to it within the subprogram. That's a compilation error. To fix this, I could modify the parameter mode to in-out. In Ada, when there are no parameters, parentheses have to be omitted. So there are actually two compilation errors here, on the function declaration and on the function call. Ada doesn't provide any forward references. In other words, when you refer to a variable or to an entity in general, this entity has to be declared prior to the usage. In this example, I should be able to access W because W is declared in the scope of P. However, because it's declared after nested, I will have no access to it. The fix here is easy. Just declare W before the definition of nested. From a syntactical point of view, this code is correct. However, at runtime, V is constrained between 1 and 2, and it's retrieving the value resulting from the call to F, which is returning a string of 8 characters. So that's going to be a runtime error. It is not possible to write an 8-character string into a 2-character variable. There is an easy fix for this one. Just remove the boundaries at v declaration so that it will take automatically the boundaries of the value that is returned by f. Overloading can only be based on parameter types, parameter number, or return type. Parameter names or parameter modes are not enough to create a situation of overloading. So in this case, the compiler will refuse to compile the second P on the ground that it is too close to the first one. In this case, the overloading is legal. There are two P procedures that are different from the type of their parameter v. One takes integer, the other one takes float. However, at call time, if I do not provide any default value, then the compiler will not be able to decide which P to call. In this very case, because of this ambiguity, it will actually not be possible to call P without an explicit value. There is no way to write a code that can discriminate on the defaults. This is just a special case though. Most of the time, there is a way to help the compiler in these situations. This is a very common problem when starting to use the language. An out parameter is a result only, which means that one cannot assume that it has an initial value. As a matter of fact, when dealing with elementary types, such as scalar, it does not have such value. It will not get the value from the calling context. So when I write r equals r plus v, the very first time this assignment is done, the r on the right hand side is initialized. In Ada terminology, this is erroneous. It's impossible to predict the behavior of this code. Some tools, such as compiler warning or the code peer static analyzer, will be able to spot those problems prior to execution. This is my personal most common mistake when overloading the equality operator. In this example, I want to have a special equality in certain situations. Namely, if L or R are below 0, I'm considering that the two objects are always equal, whatever that means in this context. Otherwise, I want to fall back to the default equality. Well, here, it's not really what I'm doing, because when I write L equals R within the equal function, I'm calling the equality between two objects of type myInt, which is this function that I'm specifically overloading. So this is going to be an infinite recursion. I'm going to call the equality between two values of my int over and over and over again. There are various ways to overcome those difficulties. In this very case, since I'm working on an integer type, I could just convert those two values to integer and use the integer comparison. In this case, I am introducing a new equality between an instance of rec and a floating point value. There is no inequality that is defined in this code. However, the introduction of an equality operator automatically creates the inequality as well. Therefore, this code is correct, There has been an inequality operator generated automatically for me. This concludes this lesson on ADA subprograms. There is actually much more to know about them. Stay tuned, new content is coming in.